Hi, everybody. Welcome to this lecture video for Math 70. Today we are talking about section 5.3, which is special cases for factoring quadratics. So just as a reminder, the box method is a useful way to factor quadratics when the x squared term does not have a leading coefficient. Something like x squared plus 7x plus 10, right? If you don't have a leading coefficient, the box method is a good thing to try. Even if you do have a leading coefficient, if you're able to first factor out that leading coefficient, then you can often do the box method on the rest of it. There are some special cases where, again, the box method will work, but it can be helpful just to recognize those special cases. So our first one, and what we're going to do is we're going to work backwards. What do I have if I have x plus 3 times x plus 3? Now, using the box method to work forward, x plus 3 and x plus 3, I have x squared, 3x in each of these window panes, and 3 squared, or 9, in the end, or in the last pane. And I put that all together, and I have x squared plus 3x plus another 3x plus 9, which is x squared plus 6x plus 9. I want you to notice that 6 is 2 times 3, and 9 is 3 squared. So when we have a quadratic where the middle coefficient is 2 times a number, and the constant is that number squared, it can factor into x plus the number times x plus the number. Let's just do another one, moving forward again until we see the pattern. So again, moving forward, let's do x plus 7. I'm going to write it as x plus 7 squared, which is x plus 7 times x plus 7. And the box method for multiplying out the x plus 7 gets me an x squared, 2 of the 7 x's, and a 7 squared, which is 49. And when I add that all together, I get x squared plus 14x plus 49. 14 is 2 times 7, and 49 is 7 squared. This also works if you have something like x minus 5 quantity squared, which is x minus 5 times x minus 5. The box method x minus 5 and x minus 5, and that's a minus. And actually, I'm going to put the minus 5 here because it'll be more obvious when we do the multiplication. X times x is x squared. X times minus 5 is minus 5x, and another minus 5x. Negative 5 times negative 5 is positive 25. So I get x squared minus 10x plus 25. but negative 10 is minus 5 times 2, or 2 times minus 5. Let me write it that way. 2 times minus 5. And 25 is minus 5 squared. So that method still works. And one more example of moving forward. This time I'm going to just give it a letter like x plus b, where b could be positive or negative. It could be a fraction, it could be a decimal. Oops, no squared there. X plus b times x plus b. And our box method. X plus b, x plus b. I have x squared, 1bx, another bx, and a b squared. And so I have x squared plus 2 times bx plus b squared. And there we have the 2b, and there we have the b squared. So now let's factor. We can always use the box method, but we don't have to. Let's look at x squared plus 8x plus 16. And we'll use the box method first. X plus. I should have an x squared here. I should have a 16 there. And so I need to look at the pairs of numbers that multiply to be 16. Don't forget that there are also negative pairs of numbers, although I don't think we're going to end up having to go that route. And then we just do our addition across. I like to put them all just to show you, but probably you'll stop as soon as you see the 4 plus 4 equals 8, which means we have a 4x and a 4x, which makes it x plus 4 times x plus 4. And so we have x squared plus 8x plus 16 equals 8 plus 4, x plus 4 times x plus 4, which is often written as x plus 4 quantity squared. Now, if we wanted to use our special cases, what we would do is we would pause before we jump into the box method, and we just do a little bit of analyzing before we do the operations. X squared plus 4x, x squared plus 8x plus 16. And I pause and I say, okay, 16 equals 4 squared. This is the easy way to start, I think. 16 equals 4 squared. And 8 equals 2 times 4. Aha, that means this must take the form x plus 4 times x plus 4. So we're recognizing a pattern to help us work a little more efficiently. Let's try another one. Let's look at x squared minus 18x plus 81. We could use a box method, but we might say, wait a minute, 81 is a square number. That is a great way to start. If you recognize that your constant term is a square number, doesn't guarantee, but you might as well check this term here, and sure enough, that's 2 times negative 9. And 81 is 9 squared, but 81 is also negative 9 squared. So that means this must be x minus 9 times x minus 9, or x minus 9 squared. So your first step could be to ask yourself, is the constant a square number? And if your constant's a square number, then is that middle coefficient 2 times the number that gets you to the square? Let's do another example. Let's do x squared plus 30x plus 100. And I say, aha, 100 is a square number. It's 10 squared. And so I check and I say, is 30, no, 30 is 3 times 10. So this is not that special case. And so I go for the box method. I'm going to take x plus, build my box. And x plus, x squared, 100. Pause. All right, let's do another example. Let's look at x squared plus 29x plus 100. And first I check the constant and I say, okay, 100 is 10 squared. So maybe it's going to work out, but no, 29 is not 2 times 10. So this is not the special case, but that's okay because the box method we can use even when it's not a special case. I just do x plus and x plus. So I should have an x squared and 100, which means I need two numbers that multiply to be 100 and add to 29, etc., etc., etc. Maybe I check as I go, because 100, there's a lot of possibilities. Aha. 4 and 25 add to 29. So I just have 4x and 25x, x plus 4, x plus 25. Still could factor it, I just didn't use the special case. One more thing to say about this special case is why is x plus 3 squared not equal to x squared plus 3 squared, x squared plus 9? It isn't. It's not equal to that. And the reason is exactly because of our special case. X plus 3 squared is x plus 3 times x plus 3, which, as I did earlier in this video, using the box method, is x squared plus 3x plus 3x plus 9. We have these additional terms because of how the distribution works. It's x squared plus 6x plus 9. So x squared plus 9 does not factor into x plus 3 squared. X squared plus 9 does not factor into x plus 3 squared because we need the 6x term. What does x squared plus 9 factor into? Let's take a look. Let's pretend I didn't know that, but I did know how to find that special case. I have x squared plus 9, and I notice 9 is 3 squared, but I don't have a 2 times 3 term, so it's not the special case. So instead, I set up my box. I should have an x plus and an x plus. I have an x squared and I have a 9, but I don't have any x terms. I have, well, I don't know if it's a 0x, but when I combine them, I don't have any x terms. So my x term must be 0 times x. So I'm looking for two numbers that multiply to be 9 and add to be 0. 1 plus 9 is 10. Nope. 3 plus 3 is 6. Nope. -1 and -9, -10. Nope. And careful, -3 minus 3 is not 0. -3 plus -3 is -6. None of these work. And in fact, even if I checked fractions, like technically I could do 2 times 9 halves, or sorry, yeah, 2 times 9 halves equals 9. But when I add them, it's not going to equal 0. There is no number pair that multiplies to 9 and adds to 0. And what that means is, since there's no number pair, there's nothing that can go here and nothing that can go here that will work. And so x squared plus 9 does not factor. Let's take a look at Desmos and see why that's the case. Using Desmos is a great way to factor quadratics. If I want to factor x squared plus 7x plus 10, I look for the x-intercepts, and they're at -5 and -2. And the x-intercepts are the opposite of the corresponding factors. So since I have a -5, that turns into an x plus 5. And since I have a -2, that turns into an x plus 2. And that exactly factors my equation. And if you glance back earlier in the video, I think this was the first example I did. Yep. No, I didn't actually factor it. I just wrote it down. I can factor x squared minus 5x minus 24, because when I look at my picture, I see I have a factor of -3 and +8. Sorry, let me say it again. I have x-intercepts at -3 and +8. And that means my factors are the corresponding opposites, x plus 3 and x minus 8. And now let's look at x squared plus 9. X squared plus 9. And what you should see is that this graph never touches the x-axis. There are no x-intercepts for this graph. And what that means is there are no factors for this function. If there are no x-intercepts for the graph, then there are no factors for this function. Let's try another one. Let's pick another square number like 25, and x squared plus 25, it's way up there. And what this means is there are no x-intercepts, so there are no factors. If we try to do x squared plus 25, we cannot find two numbers that multiply to equal 25 and add to equal 0. Because x squared plus 25 is like x squared plus 0x plus 25. There are no two numbers that multiply to be 25 and add to 0. So that is our second special case. Special case number 2 is x squared plus a squared. And that does not factor. X squared plus 4 doesn't factor. 4 is 2 squared, still doesn't factor. X squared plus 100 doesn't factor. 100 is 10 squared. Even something like x squared plus 19, that doesn't factor because 19 is, it is a number squared. It's the square root of 19 squared, but it still doesn't factor. X squared plus a squared does not factor for any a other than 0, but that's kind of a sneaky example. Okay, that's two of our special cases. We have one more special case. And it's going to look a lot like the previous one, but it is different. Let's see. We know that x squared plus 9 doesn't factor, but what about x squared minus 9? I'm going to use the box method on this and see if it can give us some intuition. So x times x is x squared as it should be, and this term down here should be a negative 9. The constant is a negative 9. So I need two numbers that multiply to be negative 9. How about 1 and negative 9, or negative 1 and positive 9? And also negative 3 and positive 3 work. And then I check my addition. 1 minus 9 is negative 8. Negative 1 plus 9 is positive 8. And negative 3 plus 3 is 0. Ah, well, x squared minus 9 is x squared plus 0x minus 9. So the negative 3 plus 3 gives me the 0x that I'm looking for. Let's try it and see what happens. I'll put a negative 3x here and a positive 3x here, which means it's x plus negative 3 and x plus 3, which would factor to x minus 3 times x plus 3. This is the factored form of x squared minus 9. And let's just double check by doing our box method again, going forward. X minus 3 times x plus 3 gets x squared minus 3x plus 3x and minus 9. And the plus 3x and the minus 3x are going to cancel, and they give me the x squared minus 9. So our special case is x squared minus a number, and that does factor. Let's try another one. Let's look at x squared minus 64. So let me use a box method, and then I'll write down our general rule based on the box method. X times x gives me x squared like I want, and then my constant term should multiply to be negative 64. So I want two numbers that multiply to be negative 64, negative 1 and positive 64, or positive 1 and negative 64. Negative 2 and 32, or 2 and negative 32, negative 4 and 16, or 4 and negative 16, or negative 8 and 8. And if these ones are the last ones I got to, but it's going to be the first one I test because sure enough, negative 8 plus 8 gives me the 0, which it corresponds to 0 of the x terms. So I have a negative 8x and a positive 8x, which means it's x minus 8 times x plus 8. So x squared minus 64 equals x minus 8 times x plus 8. And I could write that in the opposite order. I could do the x plus 8 term first. It does not change anything. So our general rule for this special case is x squared minus b squared factors into x minus b times x plus b. X squared minus 100 factors into x minus 10 times x plus 10. X squared minus 4, it factors into x minus 2 times x plus 2. Even x squared minus 1, because 1 is a square number, that factors into x minus 1 times x plus 1. This works even when the constant's not a square number. If I have x squared minus 19, well, as we saw on the other page, 19 is simply the square root of 19 squared. So that must factor into x minus the square root of 19 times x plus the square root of 19. Three special cases. I want to show you in Desmos what it looks like. So let's do x squared minus 25. And sure enough, there's an x-intercept at -5 and an x-intercept at +5. And we change those, but it doesn't really matter. And what we see is when we factor it to x minus 5 times x plus 5, those are the same functions. And if we look at x squared minus 19, that's kind of a funky number, -4.3589 and +4.3589. But I bet you that the square root of 19 is 4.3589. So I can do x minus the square root of 19 times x plus the square root of 19. And sure enough, exact same functions. All right, now I'm going to write down all the special cases so you have a list. I'm going to write them down using letters. The first one says if I have x squared plus 2bx plus b squared, and here b can be negative or positive. So I might also have something like x squared minus 2bx plus b squared. Right? These are basically equivalent. That will always factor into x. Well, I'll write them here. This first one will be factored into x plus b times x plus b, which is x plus b quantity squared. And the second one would factor into x minus b times x minus b, which is x minus b quantity squared. They're really the same case. It's just is b positive or negative, or do we use the minus sign to take care of them? That's special case number 1. The important part is that 2bf needs to be in there, because if you have, actually, let me do it this way this time. So you can see special case number 2, if you have the x squared and the b squared, but no 2bx term, this does not factor. And we're done. We stop. And the third case is if you have, instead of a plus b squared, you have a minus b squared. And here b should be positive. In fact, b squared should be positive. That one does factor into x minus b times x plus b. And the third thing to note is the box method can still work for all of these. All right, so one thing we talked about with the box method is what do you do if your leading coefficient is not equal to 1? So for example, what if I have 4x squared minus 49? Well, there's two ways to approach this. The first way is to factor out the 4, which is my general recommendation. because it turns my quadratic function into something where the leading coefficient is 1. 49 over 4, that's a rational number, but it's still a number. So I can still see this as x squared minus b squared, but now b is just 49 divided by 4. Apologies, b squared is 49 divided by 4. So this is special case number 3. And it tells me that I have the 4, and then I have x minus the square root of 49 over 4 times x plus the square root of 49 over 4. And I can be done here. If I really want to, that's okay. That's not a problem. 49 over 4 is b squared, and so I just take the square roots. However, I want you to notice the following. 49 equals 7 squared, and 4 equals 2 squared. So really, I could take the square root of 49 over 4, and that, because I can split square roots across division, is the square root of 49 divided by the square root of 4, which is 7 over 2. So I could write this as 4 times x minus 7 over 2 times x plus 7 over 2. And it looks a little simpler. They're equivalent. I'm happy to accept either. It's likely that my open math is going to want this form. That is the first way to solve it when you have a leading coefficient that isn't 1. You start by factoring out the leading coefficient. There is a second way. It's not necessary to do this, but many of the questions you will work on in this section, the second way is kind of natural. So let's look again at 4x squared minus 49. And this has an x squared minus b squared, but I could think of that first term as 2x quantity squared, because 4 is 2 squared, and x squared is x squared. So I could write 4x squared as 2x quantity squared, and then minus the 49. And now instead of an x squared minus b squared, I have a 2x quantity squared minus b squared. So if let's just make a little bit of a change and call that a squared minus b squared, where a is 2x and b is whatever the square root of 49 is. B must be 7. 2x quantity squared minus 49 is therefore 2x minus 7 times 2x plus 7. And these forms, the first one I have up here, 4 times x minus 7 halves times x plus 7 halves, is exactly equal to 2x minus 7 times 2x plus 7. And it comes from the fact that if I relax my case and I don't just call that x squared, but I give it another letter like a squared minus b squared is always a minus b times a plus b. And this rule is actually called the difference of squares. And it comes up a lot. It's pretty valuable to know that what it's called. When I don't care about what a and b are, I just think about them as the difference of squares. So I'm going to do a couple more examples this way because it takes a little bit more to see how it works. Let's do as an example 9x squared minus 64. I see an x squared term and a minus another term. So I'm going to think about it as special case number 3, a squared minus b squared. A squared equals 9x squared and b squared equals 64. So 9x squared, I can think of as 3x quantity squared, which means that a is just 3x. And if b squared is 64, then b is 8. And then I use my difference of squares formula. A squared minus b squared is a minus b times a plus b. A is 3x, and b is 8. And so 9x squared minus 64 equals 3x minus 8 times 3x plus 8, plus 8. That should be a plus. Again, it's not necessary to do it this way. You could factor out the 9 before you do difference of squares. But recognizing an x squared term minus a number is of the form a squared plus b squared, you can get there a little more quickly if you recognize this kind of special case of a special case. One more example. 7x minus 7x squared minus 43. Well, 7 is not a perfect square. 43 is not a perfect square, but it's still something times x squared minus a number. So I could let a squared equals 7x squared. And I could let b squared equals 43, which means that a should be the square root of this term, which is the square root of 7 times x. Because when you square the square root of 7, you get 7. And when you square x, you get x squared. And b should be the square root of 43, which means that 7x squared minus 43 must be the square root of 7 times x minus the square root of 43 times the square root of 7 times x plus the square root of 43. Something that really didn't look like we could factor, we actually can factor. Even though the numbers in our factored form are square roots, they're still numbers, and that still works. So our most general difference of squares case is a times x squared minus b squared equals ax minus b times ax plus b for any a and any b. I don't like that. I'm going to change this. It's true, but I would rather do it like this. A times x squared minus b squared is the square root of a times x minus b times the square root of a times x plus b. I think that's better. I'm using a capital A because it's a little bit different from the lowercase a I had before. So 10x squared minus 25 must be the square root of 10 times x minus 5 times the square root of 10 times x plus 5. If I'm so lucky as to have something like 16x squared minus 81, that's the square root of 16, which is 4, x minus 9 times 4x plus 9. Okay, so that's how we expand our difference of squares. We can do a similar thing with our special case number 1, but I don't really think it's worth the effort. If I have something like 3x squared, here's my example, 3x squared plus 30x plus 75. I could do some mental gymnastics and try to figure all that out, but instead, let's factor out the leading coefficient, which is 3 in this case. I think I did this right. Yeah, let's find out. So I'm going to factor out that 3x squared plus 10x plus 25. And now I focus on the inside, and sure enough, 25 is 5 squared, and 10 is 5 times 2. And so I can use my special case number 1, keeping track of the coefficient 3x plus 5 times x plus 5, or 3 times x plus 5 quantity squared. So I strongly recommend, if you have this middle term with x's, you do the step of factoring the 3 out first. Let's look at the middle case. How about 4x squared plus 100? Let's factor that 4 out first, and I have 4 times x squared plus 25. But I have an x squared plus 25. This does not factor because it's the plus. And so I stop. That's as much as I'm going to do. All right, that wraps it up for the special cases video, and I'll see you next time.